Let's explore two-way ANOVA. Two-way ANOVA is another technique for assessing a quality of three or more means, but for a very specific situation that differs from the situation you've previously studied, known as one-way ANOVA. In sections 13.1 and 13.2 of your textbook, you studied what's referred to as one-way ANOVA, where you have one response variable, specifically a quantitative response variable, and only one explanatory variable, often called a factor or a treatment. That one explanatory variable has several levels, and it's those levels that distinguish the different populations or conditions of an experiment and are what we believe lead to different mean values. For example, a one-way ANOVA might involve a study in which you're curious about the mean age of students, but you suspect that it differs at the several CUNY community colleges. The City University of New York has several community colleges, and let's just say for argument's sake that they have 6 different community colleges. And so you're curious as to whether or not the mean age of students at those 6 community colleges is the same, or are there differences? This is a one-way ANOVA. The response variable, the variable we're most concerned with, is mean age. That's the response variable. And we think that the college that the student attends might help explain the differences in age. And so we suspect that the means, mu1, mu2, mu3, mu4, mu5, and mu6, we're questioning whether or not they're equal, or, as we suspect, is at least one of those different, right? Are the age of students different in at least one of those colleges, or are they different at all the colleges? That's what we want to investigate in a one-way ANOVA. So how is two-way ANOVA different? In two-way ANOVA, in the end, we're still going to be looking at comparing 3 or more means. We still have one specifically quantitative response variable, but in situations where we require two-way ANOVA, it's because we have 2 explanatory variables or factors and treatments, or oftentimes with experimental design. In experiments, they're referred to as, one is referred to as the treatment and the other one is referred to as the block. What do I mean by this? 2 explanatory variables. So for example, suppose that you are concerned with the time it takes students, or anybody, right? Let's just say time it takes adults to complete some kind of assessment, some kind of quiz or something like that, right? I don't know, maybe it's the driver's test. Maybe the DMV is concerned with how long it takes people to complete the written form of the driver's exam, right? And they wonder if it differs based on the time of day when someone takes the exam, and maybe that's morning, afternoon, or evening, as if the DMV is open in the evening. Let's go with me here. But they also suspect that the conditions in the room where the people take the test, assuming they're taking it in person, might have an effect. And so they also want to look at let's say, temperature in the room, right? Maybe they're trying to determine, what's the ideal temperature for giving the test. And so let's just say a low, medium, or high temperature, right? And so when let's say we run an experiment, right, where we give some people, we give the assessment to participants at different times of day and different temperatures in the room. And we set up an experiment such that we mix these up, right, where we give some people the assessment in the morning at a low temperature, and in the morning at a medium temperature, and so on and so forth. We'd have a bunch of pairings here, right? Like the last one would be evening at a high temperature. And so we get these crossover groups. And so if you run your experiment where, you're using these mixed up groups here, then you have no choice but to do a two-way ANOVA. Let's look at a more sort of realistic example. But again, just to illustrate what makes this two-way ANOVA, we have one response variable here, that's time to complete the assessment, but two explanatory variables, the time of day and the temperature in the room. Okay, both at several different levels. Let's look at a more sort of the overall structure of two-way ANOVA. In a two-way ANOVA, you'll have one quantitative, I want to keep emphasizing that, one quantitative response variable measured at the levels of two different factors. Let's call them A and B. And so the data is going to be organized, usually organized as you see here. Factor A has several different levels. Let's say that it has A levels, right? That's one factor. Factor B has several different levels, right? Let's say that there are B levels. So in the example with the time of day and the temperature in the room, that would be factor A, and it had three different levels, morning, afternoon, and evening. And factor B would have been the temperature in the room, which also had three levels, low, medium, and high, right? And so when the data tends to be organized here this way, and then within each grouping, right? So this is sort of factor A level 1, level 1 of factor A and level 1 of factor B, and then there are N observations in that group. It's not required for you to have the same sample size in each group, but it does make the analysis a little bit easier. So this right here then would be level 2 of factor 2 and level 2 of factor B, right? And so on and so forth, okay? So you get all these different mixings and all these different groups. Just some language here. When your data is organized this way, we call factor A the row factor and factor B the column factor, right? And so there are A rows and B columns. And often this is referred to as an A by B. I'm putting the word by for the multiplication symbol, A by B factorial design. Okay, why A by B? Because you end up having A times B is the number of distinct groups when you look at all the different mixings, right? So in the example before, with time of day and temperature in the room, if I have morning, afternoon, and evening, mix that up with the temperature in the room, low, medium, and high, right? We get 3 by 3 or 9 groups. So we call it a 3 by 3 design. Let's look at a more concrete example here. This is an example of data from some maple sugar producers in Vermont. They set up a testing program to determine the benefits of a new fertilizer. They took a random sample of 27 maple trees altogether, and they were treated with one of 3 levels of fertilizer, but they decided to split those 27 trees up into 3 groups of 9 to sort of test each different fertilizer type in each of 3 different climatic zones. And so the type of fertilizer here is the row variable. You see that it has 3 different levels. And then the climate zone also has 3 different levels, southern, central, and northern. And so then what they did is they did 3 in each group, right? You've got 3 low fertilizer in the southern zone, 3 low fertilizer in the central zone, 3 low fertilizer in the northern zone, and these numbers represent sap production. Okay, so that's sap production at low fertilizer. Amount of sap produced is the response variable. So all those numbers represent sap production, but based on different fertilizer levels and different climate zones. So as you can see here, they have 9 trees tested with the low fertilizer, just over the 3 different climate zones. Similarly, you could say that they have 9 trees that were tested in the central zone. Some were low fertilizer, some were medium, some were high. And so in the language of analysis of variance, two-way analysis of variance, we would say we have a 3x3 factorial design because there are 3 levels of fertilizer and 3 different climate zones. That produces 9 different groupings, right? And notice in this experiment that the response was replicated or measured. The response area was measured 3 times in each group. Right here, for example, this group here, right? These are 3 different trees whose sap production, 3 different trees, the sap production for 3 different trees with high fertilizer in the northern climate. Okay, so I hope you can sort of understand how this data is laid out here. We would say that n, or lowercase n, equals 3. We have a sample of 3 trees in each of the different groupings of the factors. And again, we have a row factor, in this case is the fertilizer, and the column factor is the climate. Okay, so take a minute, pause the video, which it'll be paused for you, and answer the following question. Based on this example here, what is the row factor? This is a 4x4 design. Quality rating is the response variable. You have 2 factors. Which one is the row factor? Okay, so now that we've sort of established some of the language and the way that the data is laid out for analysis of variance two-way, let's go back to this example here with the sap production of trees that produce maple, right? So maple trees. And let's think about what the question of two-way ANOVA is. Remember that two-way ANOVA is about assessing the equality of means. And so, if you kind of read through this example again, you can see that there's really kind of 2 different questions, 2 different main questions. And these questions are referred to as sort of the questions about the main effects. Right? The questions about the main effects. We've got 2 explanatory variables, so there are really 2 questions. Does the fertilizer or the level, right, or the type of fertilizer affect the amount of sap produced? And the second question is, does the climate zone affect the amount of sap produced? So those are the 2 big questions that we generally want to ask when we have these types of experiments or studies done. We're looking for the equality of means, but when we have essentially a crossover of 2 different explanatory variables, and you might think to yourself, oh, okay, well, just start with looking at the different fertilizer levels. So take this sample of low fertilizer levels, this sample of medium fertilizer levels, and this sample of high fertilizer levels, right? So take those 3 samples, call it X bar low, X bar medium, X bar high. And eventually, those numbers are measured and looked at specifically, and that will help you understand if there's a fertilizer effect, right? If based on these sample means are then the population means for all the maple trees going to be the same. You could do the same though for the each climate zone, right? You could separate it into 9 trees in each climate zone and do a similar thing. But there's a problem with separating this data. Okay? There's a problem with separating this data. And the problem with separating this data is defined here, and it's what we call the interaction effect. There are good reasons why experiments and statistical studies are set up this way, to look at 2 variables or to study 2 explanatory variables at one time. Again, there's lots of reasons why we would do that. But when we do that, we sort of limit ourselves from separating the factors, potentially because of what's referred to as an interaction effect. And it's this question of what if the combination of fertilizer level and climate zone, what if they're affecting one another, right? What if low fertilizer is behaving differently across the 3 zones? right? And what if it's behaving differently across the three zones in a very different way that the high fertilizer is acting across backwards across the three zones, right? That's called the interaction effect. If each if the level of each factor is sort of producing means in different ways across the levels of the other factor, then we have an interaction effect, and we really should not, right? So if there's a significant interaction between the factors, the levels of the two different factors, then we really shouldn't separate them. Then we really need to kind of just look at this as a whole instead of separating the two factors out separately. And so when we look at an example like this, before we get to that, the first thing we want to do is we want to do some kind of statistical test to determine if there's an interaction effect. In other words, there's some kind of interaction between, in this example, fertilizer level and climate zone that really would stop us from separating those two factors. If there's not, right? If the statistics tells us that there's not an interaction between those two variables, what that means is that then it's okay to separate out the two factors, and we do in fact get essentially two new hypothesis tests, one for each factor. So in this example, the question of does the level of fertilizer affect the amount of sap produced essentially boils down to, would the mean sap production be the same at all fertilizer levels? So we would have a null hypothesis that the mean sap production at the low fertilizer is equal to the mean sap production of the medium fertilizer trees is equal to the mean for all trees treated with high fertilizer. Notice it's basically what a hypothesis, null hypothesis would look like in a one-way ANOVA. And then the alternative hypothesis would be that the mean sap production is different at each, or at, I'm sorry, not each, at least at, or let's say for, don't want to use at. The mean soap production is different for at least one fertilizer level. So that would be the hypothesis test for checking whether or not there's a fertilizer effect, okay? And then to determine if there's a climate zone effect, the null hypothesis would be that the mean for the mean sap production for trees in the south is equal to the mean sap production for trees in the central, which is equal to the mean sap production for trees in the north, against the alternative hypothesis that the mean sap level, or the mean sap production, is different for, or in, at least one climate zone. So we end up really with three hypothesis tests here. One for interaction that we do first, two for the row factor, and the third one for the column factor. So in general, in a two-way ANOVA, we have almost sort of three different hypothesis tests. Now, you'll notice that these are not written in terms of means, even though that's what ANOVA is for, testing equality of means. They're not written that way because to write them in general, how many means do you have, right? It becomes complicated. So we always start with the interaction test. Null hypothesis says that there is no interaction. The alternative is that there is an interaction. We always start with that. So if we reject the null hypothesis here, if the null hypothesis of no interaction is rejected, then we do not go to the hypothesis test involving the main factors, right? These are the main factors. Because in essence, the presence of an interaction between the factors is, here on the slide it says clouding the interpretation of the main effects. I might use the word confounding. That may be a more familiar word to you, right? It makes it hard to separate or really determine whether or not each factor has an effect on the response separately. But if we fail to reject the null hypothesis, it doesn't mean there's absolutely no interaction, but it does indicate that that we don't have evidence that there is. So we'll go ahead and we'll do the test for the two main effects. And again, this is equality of means across the levels of both factor A and factor B, right? The row factor and the column factor. So the null hypothesis of no effect would mean that the means are equal, and that there is an effect would tell you that at least one mean is different. Okay, and that's the same for the test of both main effects. So overall, just to kind of put this in the context of the structure of every hypothesis test, you're always going to start with stating your hypotheses. That's what I just described on the last couple of slides. Then you're going to look at your conditions, and we'll get back to that later. Okay. Just like conditions for one-way ANOVA, conditions for two-way ANOVA are a little complicated, so we'll save that for later. Then we're going to have to calculate a test statistic and a p-value. The test statistic is referred to as an F statistic because the p-value is from what's called an F distribution, same as one-way ANOVA. It's a right-tailed test. It's a right-skewed distribution. It has two different degrees of freedom that determine its exact shape, and those degrees of freedom are based on the overall sample sizes and the number of factors of each factor. So there's three different tests, right? So three different tests. So there are three different test statistics and three different p-values. But when you carry out an ANOVA analysis with statistical technology, it's all going to come out in one ANOVA table, right? Remember, an ANOVA table from one way, a two-way ANOVA table is going to just have more stuff in it. Remember to always look at the interaction test first, and if we do not reject, then we can look at the results for the other test. So once we get our test statistics and our p-values, then our decision rule is always the same. If the p-value is less than alpha, we reject the null hypothesis and conclude that there is a significant effect of the factor on the response. If the p-value is not less than alpha, we do not reject the null hypothesis, and therefore there is no evidence of a significant effect of the factor. Right? So that's the general structure of a ANOVA hypothesis test. So pause here. This is the same example from before where you have, what are they measuring? They are measuring the ratings on the quality of dormitory environment, but they are looking at the ratings. So all of these numbers here are ratings that students gave, but it's broken down by the class, right? Freshmen, sophomores, juniors, seniors, so the year in college, and then also broken down over the four different dormitories. So we're looking at ratings and whether or not ratings are different based on the year in school and the dormitory. So there will be three tests in the two-way ANOVA. Which one of the ones listed here is not a hypothesis test based on this information? Sort of jumping a little bit to the end here, not really showing you where these numbers come from. You should be familiar here with the SSMS, sum of squares, mean squares. Remember, it's three different tests, and this is the same language and notation as with one-way ANOVA. But when you do or you run or ask StatCrunch to do a two-way ANOVA, you're going to do that by going to stat ANOVA two-way, and this is going to be the output. Okay, so what I'm showing you here is the output when you run a two-way ANOVA in StatCrunch. And so I want to jump to this before really kind of looking at the input, like how do you get to this? You do have to have your data organized in a very specific way, and we'll come back to that. But just take a look at the ANOVA table specifically here. Okay, notice that there is a row for interaction, and so this is your test statistic and p-value for the interaction test. So the p-value for the test with the null hypothesis that there's no interaction effect, in this case, is 0.0336. Okay, and then depending on our significance level, that may or may not be significant. If that's not significant, if that's too big of a p-value, then we would look specifically across at the row factors significance. There's your test statistic and your p-value. Pretty small p-value there for the row factor. And then you can also look at the column factor. There's your test statistic and your p-value. Okay, so just like a one-way ANOVA, you look at the ANOVA table for the test statistic and p-value for the specific factor that you're looking for. Okay. Back to the example with the maple trees, where we're interested in sap production based on fertilizer level and climate zone, right? We always have the test for interaction, right? Remember, there's always the problem, so we always test for interaction first. Okay, always test for an interaction first, but then if we fail to reject the test for interaction, then we can break it down to these two separate tests. We can separate out the factors, the row factor, in this case fertilizer, and the column factor being climate zone. So I'm going back to this because we're actually going to do the ANOVA analysis of this now. This way that the data is organized is, in this type of table that I showed you before, is the typical way that people display the data for a two-way ANOVA test, just because it really nicely lays out sort of the different groups, in this case the 9 different groups, right? But when you want to, right, here's one of the 9 different groups. But when you want to put this data into statistical software, our data is typically not organized this way, right? We don't often, and particularly with StatCrunch, we can't label our rows like you see here. And so if you were organizing this data into StatCrunch to do an ANOVA test, this is what it's going to look like. Notice in the first column here, and the order of the columns doesn't matter, but here I have the sap production, which is the response variable data. All of the numeric values, right? Those are listed in one column. And then then I have a column that indicates the row factor, right? The level of the row factor, and then another column that shows the column factor. I know that sounds weird, but in this case, right, the row factor was fertilizer. So in the second column here, you see all the fertilizer levels. So let's just take, let's do it this way here. The climate zones, the way I organize this. Look at these first 9, right, are all in the southern climate zone. 3 that are low, 3 that are medium, 3 that are high, right? So let's just take this southern medium, 88, 94.1, and 93. Let's go back and check that, 88, 94.1, and 93. Southern medium, right? Southern medium, 88, 94.1, and 93. Okay, so just check your data. So that's the southern, and then notice we have then the central, right? There should be 9 rows for central, 3 low, 3 medium, 3 high. You can do this in any order that you want in terms of the order of the columns, but just make sure that everything's labeled correctly, okay? And so then when you want to then go to Stat, ANOVA, two-way, okay, you've got your data in StatCrunch. Now you want to actually ask it to do the analysis. You hit Stat ANOVA two-way, and this is what the input box looks like. Okay, these are your inputs. You have to tell it where the responses are. So that's where the column where the data for the response variable is. Then you have to tell it where the row factor is indicated, right? In what column of your data set is the row factor located in, and then in what stack crunch column is your column factor located in. Okay, so you have to basically tell it what the response variable is, what the row factor is, and what the column factor is. And then we'll come back to this later, but always make sure you check off plot interactions and compute the Tukey. It's the same Tukey, well, similar Tukey as what we started with one-way ANOVA. We'll come back to those later. Okay, so but to get the ANOVA table, you at least have to tell it the response variables. The row table that we saw before was actually the ANOVA table for the sap production on the maple trees experiment that we were looking at. So sap production is where my data was. The fertilizer column is expressed my row values, and the climate zone column showed the different climate zones for my data. So notice we have the two different main factors, and then the interaction effect. So we have the test for the main effects, and we have the test for the interaction effect. Remember, we've said that we always check the interaction effect first. So I slide over my degrees of freedom, the sum of squares, the mean square, the test statistic for the interaction effect, and then the p-value for the interaction effect. So for the interaction effect, the null hypothesis is that there's no interaction effect between fertilizer level and climate zone. The null hypothesis of that test is that there is an interaction effect between fertilizer and climate zone. And so let's just say, I don't think a significance level is given, so let's just say at alpha equals 0.05, which is the most common significance level, at alpha equals 0.05 with the p-value of 0.0036, right, which is less than alpha, we reject the null hypothesis and conclude that there is evidence of an interaction effect. So those other two hypothesis tests that we wanted to do cannot be done. Cannot test for main effects separately, right? Does that mean that there's nothing you can do? No, but what you would do from this point is beyond the scope of this class, okay? So for the purposes of this class, if you reject the null hypothesis of interaction, then you would conclude that there is an interaction effect, and we do not go on to the test for main effects. Now, one sort of follow-up in this particular case about the interactions is to construct what are called interaction plots, and we'll come back to that a little later. For now, let's look at another example. Okay, so here we have data on birth weight of babies born to mothers in various ages who followed different diets in their first trimester of pregnancy. So we have an obstetrician who wants to determine the impact of 3 different experimental diets. So what they want to understand is the impact of the diets on birth weight. So our response variable is birth weight. So all those numbers you see in the table there are the birth weights of the babies. So they randomly selected 27 mothers in their first trimester, of whom 9 of them were 20 to 29-year-olds, 9 of them were 30 to 39-year-olds, and 9 of them were 40 years or older. For each age group, then they assigned the mothers to one of 3 diets. So The ages would be, if you remember the language of experimental design from 1.6, the ages would be the blocks. We have a block design here. The main explanatory variable are the 3 different diets, but they're experimenting with those diets on mothers of various ages because they have reason to believe that age also affects birth weight. So they take mothers at these 3 different ages and make sure that they have each diet tested within the 3 different age groups. Okay. And so jumping down to B and C, jumping down to B and C, B says determine whether there's a significant interaction between age and diet. They're asking that first because we should always check that first. So testing for the interaction effect. The null hypothesis would be that there is no interaction between age and diet. Against the alternative hypothesis that there is an interaction between age and diet. Forgive me for being lazy and not copying those words over. And so we're going to test that first, and then notice the language of part C. If there is no significant interaction, determine whether there's a significant difference in the means for the 3 age groups. If there's no significant interaction, determine whether there is a significant difference in the means for the 3 diets. And it's this last one that I think is really core to what they're trying to study here. So this part C then gives us 2 different tests, or the tests for the main effects. The first one, which would be our row variable, the null hypothesis would be that the means are the same for the 3 different age groups. So I'm going to write 20s, 30s, and 40s plus. And the alternative hypothesis would be that at least one mean is different. At least one mean is different. Right? And so just in the typical language of two-way ANOVA, that's, technically what we're testing. The null hypothesis, though, says that there's no age effect on birth weight. Right? If the means are the same, that means the birth weight's the same across 3 different age groups, so that age has no effect on birth weight. And the alternative hypothesis is often just written as that there is an age effect on birth weight. Okay, so you'll oftentimes see those hypotheses written 2 different ways. And so now for the column variable, which is diet, right, which is really their main focus, I think, based on what's described at the beginning, the null hypothesis, I'll go right to, would be that there's no diet effect on birth weight, right, which implies that the mean for diet 1 is equal to the mean birth weight for diet 2 is equal to the mean birth weight for diet 3, against the alternative hypothesis that there is a diet effect on birth weight. Again, just writing it 2 different ways, that would then imply that at least one mean is different, and here specifically across the diets. Okay, so these are the 3 hypothesis tests, and we're going to get the results of all 3 of them in an ANOVA table by going to we're going to do stat ANOVA 2-way. Now, it flashed on the screen before, and you're going to see it in just a second. I pulled this data right out of what would have been a question just like your MyLab homework, and you've probably seen this happen before, right? Like there was a little box next to my data in my online homework, and when I clicked on it, I chose open in StatCrunch, and here's what it looks like in StatCrunch. Okay, so a little bit odd. Here's what it looks like in StatCrunch. And so what in the world is going on here? right? So if you read carefully about the experiment that was performed, they really want to know about the diet and its effect on birth weight, right? So the diet would be the treatment. Notice there were 3 diets: diet 1, diet 2, diet 3, diet 1, diet 2, diet 3, etc., etc., etc. This is cut off a little bit. And then the value, right? These numbers, what are the numbers? These are the numbers in the table. Those numbers are the birth weights. Okay, those numbers are the birth weights. And so then, just clean this up a little bit here. Those numbers, or what StatCrunch is listing as value, are the birth weights. And then the blocks, they're using the language of experimental design here. The blocks are the 3 different age groups, right? They tested the diets across every age group. And now notice here they're using 1 and 2, and then eventually this data goes into 3 because there are 3 different age groups. So how do I know which is which? I have to just be careful here and check it against my data. So notice in treatment 1, right? So diet 1, I've got the numbers 4473, 3878, and 3936. Where do I see that? That's right here, right? Diet 1, age 20 to 29. And just let's check that again. Age group 1, right? So if age group 1 is 20 to 29, then under diet 2, the number should be 3961, 3557, and 3321, which of course it is. Okay, so that's so block 1 is the 20-year-olds, block 2 is the 30 to 39-year-olds, and then what would follow below would be the 40 plus in block 3. So sometimes this will happen. It's just the way that whoever put the data into StatCrunch coded it to go along with your homework questions. So just please keep an eye out for that. And listen, when you get into StatCrunch with the data, if you want to change the words block, treatment, and value to age, diet, and birth weight, knock yourself out. So the responses are in the column for value because that was birth weight. Okay, I have to tell StatCrunch where to find the data. Then I have to tell it where to find the values of my row variable, which in this case would be age, or the blocks here. And then I have to tell it where to find the values of the column factor, which in the organization of the data is the diet or the treatment. I'm going to choose plot interactions and Tukey every time, even though we haven't talked about those yet. And let's take a look at the results. Okay, and so here are our 3 tests. The test for the different blocks. Remember, block was age, so the age effect. And then we have the test for the treatment, which is diet, is right here. And then we have the one that we should look at first, which is the test for interaction, is right here. Okay, so the test for interaction, that one we should always look at first, right? And so we look at it. Did they give us significance level? They didn't give us significance level, so let's say at alpha equals 0.05 as usual. We look at the interaction test. It has a p-value of 0.8801. So with a p-value of 0.8801, which is greater than alpha, we do not, we do not reject the null hypothesis, which means that we do not have evidence of an interaction effect. We do not have evidence of an interaction effect. Okay, we don't have evidence that there is an interaction effect. And so that means that we can test the main effects separately. And so for the main effects, right, so for age, which the hypotheses were written before, what's the p-value for the age effects? The p-value is 0.0424, which is less than alpha. So we would reject the null hypothesis. So if you want, take a minute to go back a slide or 2 and look at the null hypothesis and alternative hypothesis for the age effect. When we reject the null hypothesis, that means we have evidence that the mean birth weight for at least one age group is different. So in other words, there is an age effect. There is an age effect. And then for the one they really wanted to know about, right, the diet, for the diet effect, spell that right, for the diet effect, okay. For the diet, the p-value is 0.0004. Wow, that's a really low p-value, right? 0.0004, which is, of course, less than alpha as well. So again, we reject the null hypothesis. So there does seem to be, we have evidence. And this time I'm going to steal the language from the question itself, that there is a significant difference in the means for the different diets. We have evidence that there is a significant difference in the mean birth weight. I added that word in there. I always like to remind myself what my response variable is. There is a difference in the mean birth weight for the diets. So there is a diet effect on birth weight. Right? So when the p-value is small, that means that particular explanatory variable does appear to have an effect on the mean value of your response variable. Now, that is how we do a two-way analysis of variance. But there's still a couple of open-ended questions. Before we get into that, take a look at this example again. This is the data on quality ratings based on different dorms and different years in school. And so based on the ANOVA table given, can we say that there is significant evidence that the mean quality ratings differ by dormitory at the 0.10 level of significance? Hint, we always look at the interaction effect first. And if there is a significant interaction, then we do not proceed to testing the main effects. So take a minute to answer this question. In the situation where we have a significant interaction effect, then we will not proceed to look at the main effects separately. We will not be testing the equality of means based on the two different explanatory variables. But that doesn't mean we don't know anything in that case about the way that the two factors interact, so to speak. And so we often construct what are called interaction plots. An interaction plot is a plot or a graph, right? A plot or a graph of the mean for the response variable in factor A at each different value of factor B, and vice versa. So let me show you an example of what that looks like, and then I'll come back to the next two bullets here. So these are interaction plots for the maple trees and the sap production. So I want to specifically just look at the one on the left here. What we have here, based on the three different climate zones. Okay, based on the three different climate zones, each line represents the different fertilizer level. For example here, I'm going to write over the low fertilizer in red. So the mean sap production for low fertilizer in the central zone. Low fertilizer central zone. Low fertilizer central zone. If you find the mean there, sample mean, it should be about 85, maybe just under 85. If we move over to the northern climate zone and find the mean there, so the mean for the northern, that then is a little bit less than that, right? And so they're connecting that with a line. And then if we move back to the southern zone and take those three and find the sample mean, it looks like that is way lower in the south. I don't know, maybe almost 70, 75, 76 right? So we can see that for low fertilizer, the central and the north seem to have about the same average, but then it's way less for the south. Take a minute to think about what I just said. Because I want you to contrast that then for the medium and the high fertilizer levels and how it differs over the climate zones. So I'm going to go over these in black. Okay, so in both the high fertilizer, which is the line that kind of starts in the middle right here where I put the star, notice that as you move from central to northern, it drops much more significantly than it did for the low level of fertilizer. And then between northern and southern, it actually goes up, right? Now that in the central to the north, it drops. And then from north to south, it goes up. That pattern is the same in both the high and the medium, right? But it's a very different pattern. Clearly, in the northern zone, for high and medium fertilizer, the sap production is way lower than what it is in the central, whereas opposed to for low fertilizer, they're about the same. And so right there you can see the interactions, right? You can see that high and medium fertilizer levels sort of behave very differently across the climate zones than the low fertilizer. And a quick way to spot that is to use kind of this rule of thumb here that was on the last slide. If you see parallel lines, like if all the lines you see in an interaction plot are parallel, then that indicates that there's no significant interaction. Now, of course, you would have to do the ANOVA test to know that for sure and look at a p-value. But by looking at an interaction plot, we do get a sense for whether or not there's a significant interaction, whether it looks like there is, and then if it looks like there is, right, that would be if the lines are not parallel, as we saw in the sap production example. The lines were not all parallel. I would add the word all in here. The lines were not all parallel, which means that there's a significant interaction, which of course we'd have to officially test with an ANOVA. But if there's a significant interaction, that ends the test, but the interaction plot can then tell us sort of like how, right, or what kind. And so in that example we were just talking about, we can see from this interaction plot that the low fertilizer seems to be behaving very differently over the climate zones than the high and the medium fertilizer. So we do get a little bit more information when we have a significant interaction by looking at an interaction plot. But nothing concrete. This is looking at interaction plots kind of equates to what we did with one-way ANOVA when we had when we looked at box plots to really compare the values across the different factors or the different treatments. Okay, and then finally, one last thing to talk about here, and that's something I skipped, and that's the conditions for the ANOVA test. Specifically the two-way ANOVA test. So 3 major conditions here. The populations from which the samples are drawn must be normal. So of course we can look at normal probability plots and do a correlation check, right? QQ plots. The samples must be independent. So a lot of the time we just have to sort of assume that that's true based on the scenario described of the experiment or the statistical study. And then the third condition is that the populations must have the same variance. Similar to the one-way ANOVA, sort of a rule of thumb here for that one. It's impossible to check for the population variances, but we can just sort of make sure that the largest standard deviation is not larger, so less than or equal to twice the smallest standard deviation. Right? So the standard deviation max is less than twice standard deviation min. I have another, what seems like requirement here. Technically, it's not a requirement, but if we have an equal number of observations for each combination of the factors, the test becomes more powerful and reduces the likelihood of a type 2 error. So while it's not officially a requirement, it is usually preferred. I want to just take a minute. You should know how to do QQ plots and check the correlation for normality. But I want to take a minute to talk about how to check the standard deviations for these, like the variety of different groups, right? I just want to end here by kind of showing you how to do that in StatCrunch. So in the example with diet and age, the diet and the age groups, right? We have a 3x3 experimental design, which means we have 9 different groups. Okay, so I'm going to do summary stats with birth weight, right? That's my response variable. So I'm going to pull in birth weight. I'm going to group it by the mother's age, right? Those are the blocks. I'm going to group it by mother's age, but I'm going to do this 3 times. First, I'm going to do it, and I'm going to use the where builder, where diet equals diet 1. Then second, I'm going to do it where diet equals diet 2. And then I'm going to do it a 3rd time. I'm going to run this analysis 3 times. You can't do this all in one. This is 3 runs of the summary stat analysis. The 3rd time it's going to be when diet equals the value diet 3. Okay, and you could just ask for the standard deviation, but I asked for the mean and the sample size as well. And so the first run gives me this, the second run gives me this, and the 3rd run gives me this. And here are the standard deviations for the 3, 6, 9 different groups. Of those 9, you can find the smallest, right? That's right here, the smallest. Looks like 227. Yep, 227. That's the smallest. And the largest looks like 420. And so I want to compare these two. So this is S minimum and this is X maximum, right? So is the maximum 420.68? Is that less than or equal to twice 227.8? The big question mark there. And actually, I think the answer is no. So for this test, the condition was actually not met. Sad face, right? But we did the test anyway. And this just goes to show you that if you don't check your conditions, you can always run the test and come up with a conclusion, but that conclusion then is not necessarily completely grounded in statistical theory because the conditions are not met. The conditions tend to be a bit robust, which means a slight departure like we have here isn't too bad, but please make sure you check your conditions. And that, my friends, is 2A ANOVA. Oh, and I lied. I said we were done. One last thing here. The Tukey test is a follow-up. So you can add a Tukey test when you run the ANOVA, the 2A ANOVA or the 1-way ANOVA. The p-values that you'll see in the Tukey test results are for a two-tailed equality of means test. And then you'll also see lower and uppers. Those are confidence interval estimates for the difference in means. So let's just take a look at the diet, because that's what they felt was most important, right? And this is the data on the age of the diet and birth weight. So the setup of the Tukey test here is very similar as it is for 1-way ANOVA, because it's splitting up the factors, right? So diet 1 compared to diet 2. So the mean birth weight for diet 1 minus the mean birth weight for diet 2. The confidence interval, we say it's approximately negative 1,030 if I round to the whole number, to negative 249. This was grams. Notice that 0 is not in the interval. So that means that there is a significant difference for diet 1 and diet 2. And also notice that it's negative, right? Which would make mu1 less than mu2. Similarly, we can compare mu1 to mu3. We get a confidence interval from negative 1076.6 to negative 295. Again, when we look at the difference between mu1 minus mu3, 0 is not in the interval, so there's a significant difference, and the values are all negative, which would imply that mu1 is less than mu3. And then finally, we can compare mu2 to mu3. The confidence interval is negative 437 to positive 343. So when we look at mu2 minus mu3, 0 is in the interval, which tells us that there's not a significant difference. So it appears that mu2 might be equal to mu3, but that they're both less than mu1. So the Tukey test kind of gives us a way of comparing which means are different. Writing at the top of the screen here, you might remember some notation from one-way ANOVA when we're looking at mu1, mu2, and mu3. It appears that mu1 and mu2 are probably the same, but different from mu1, and the underlines indicate that. And that, my friends, is finally a wrap-up on two-way ANOVA. One last question. Here are two ANOVA scenarios. Which of these is a two-way ANOVA? Question 1 or question 4?